This is the next video in the series about integrated rate laws. So far, we've looked at what the integrated rate law and the half-life formula are for each of the 0, 1st, and 2nd orders. We've practiced plugging different kinds of data into those integrated rate laws, and now, as promised, we're going to look at some data sets and see what kind of integrated rate law information we can get from those. So let's start with this first example. I'll give you a second to write it down. So this one says, identify the order, the value of K, the rate constant, and the initial concentration from the plot. So here's our plot, and we can see that there's a line. So this is a linear relationship, whatever order this is. We're given the equation for the line, so we can take some information out of it, and we can see what the y and the x-axes are. And the reaction being modeled here is B goes to product. So B is our only reactant. So remember, paying attention to the y-axis gives you the most amount of information from the plot. When we're trying to identify the order, we want to find out what variables plotted against each other will give us a linear relationship. So here we can see that 1 over the concentration plotted versus time gives us a straight line. We can look back at our notes, see what order that should correspond to. Here's our picture from the previous video. We said 1 over concentration versus time. Linear relationship should be a 2nd order. So this is going to be a 2nd order relationship. So far, so good. Okay, the next part said to find the value of K. And I can find the value of K from the rate law or from the integrated rate law, but the integrated rate law is related to the variables in this linear equation. So I'm going to go with the integrated rate law. And now that I know the order is 2nd order, I know which one to pick. Integrated rate law is going to be the most useful because it has the time variable in it, just like our plot. So the 2nd order integrated rate law we can get from our reference table here. 1 over concentration equals KT plus 1 over concentration. So 1 over concentration at time t equals K times T plus 1 over initial concentration. And that's related to the equation for the line, like y equals mx plus b. So the first number that we want to know is the value of K. And so we can see here that K is going to be the slope. And remember that K is always the absolute value of slope because K is always a positive number. So in this case, our slope is 0.5 and it already is a positive number. So that's fine. And we should probably find the units. I was lazy and I didn't write the units. So the units for 1 over concentration should be 1 over molarity, and the time is in seconds. And I always find the easiest way to find the rate law, to find the units are from the rate law. So you can do it that way, or you can take it straight out of the plot. So if you took it from the plot, you would have y over x, 1 over molar divided by seconds. So there's our unit, 1 over molar seconds. Or you can do it with the rate law, like me, 2nd order rate law. Rate equals K times A to the 2nd. We know the rate should have units of molar per second. We know that each of the concentrations will be a molarity, and there's 2 of them. So if we want to find the value for K, we need to cancel out these units. So it would be 1 over second time molarity. So you can take it straight out of the plot, or you can take it from the rate law. Okay, and then the third thing we're looking for is the initial concentration. And we know the initial concentration is related to the intercept. It's not necessarily equal to the intercept. So the y-intercept from our plot is going to equal 1 over the initial concentration. And according to our equation for a line, y-intercept is 10. So remember, we have to do a transformation. We can't just take the 10 straight out of the plot. So our initial concentration is going to be 1 over 10, or 0.1 molar. And this one, there we go. Beautiful. So we use this plot to define the order, the rate constant, and the initial concentration. Okay, that wasn't too bad because we were given the plot and we were given the equation for the line. But sometimes you're not given the equation and you're not even given the plot. Sometimes you were just given the raw data. And if you have great plotting skills, you can draw the plot and you can use it in the way we did before. If you are good with your calculator, you can make it as a list and you can find the equation for the line from your calculator. But if you're a mere mortal like me and like the rest of us, you don't have those skills and it would be easier to just look at the slope. So let's look at how we would solve from a concentration and time data set. So here's the data set. Please take a second to write this down. We want to find the order of the reaction using this data. So this looks kind of empty and looming, but remember what we know. We know that we can find an order based on the linear relationship. So we're trying to figure out whether concentration versus time is a linear relationship, and if that doesn't work, because that's the easy one, we can check natural log of concentration versus time and 1 over concentration versus time. But we don't have a line, right? We just have some data. So how would I know if this data represents a line? Well, what do we know about lines? We know that a line only has one slope. And it has that same slope between every pair of points. Oops. Has the same slope between each pair of points. Right, if we had some line, the slope between these 2 points and the slope between these 2 points should be the same slope. I guess it's a negative slope. So what we are going to do is we're going to pick 2 different sets of points and we're going to calculate the slope at each of them, and then we're going to compare. So our strategy find the slope of 2 pairs and compare. Look for matching values. So we're going to try each of those 3 tricks: concentration, natural log of concentration, and 1 over concentration. And we're going to take the slope of 2 pairs for each of those types of y variables. And we're going to look for the case when the two slopes are the same. So this is essentially a guess and check. But we don't have to guess for the entire data set. Finding all of those transformations for the entire data set takes a lot of work. So I'm just going to pick a couple of data points. So I'm going to pick the first 2 points and the last 2 points. You can pick whatever 2 sets of points you want. I just like to pick some that are significantly far apart, because sometimes if you have a curvy line, slopes of points near each other are still pretty close, but they shouldn't be close for a curvy line if they're far apart. So I'm going to be super sure by picking opposite pairs, but it's fine for either. Okay, so for 0 order, we expect to see a straight line for concentration versus time. That's the easy one, right? Plotting the data the way it's given should give a line. So we always test 0 order first. All right, so the slope of my first pair of points is going to be change in concentration over time. So 0.80 minus 1 over 25 minus 0. And that is going to give me negative 0.008 as my slope. And then we'll try it for that second pair of points down here. So 0.33 minus 0.4 divided by 200 minus 150. And that should give me negative 0.0014. There we go, just barely fitting. Okay, so our numbers are 0.008 versus 0.0014, and those are kind of close together, but I'm not really happy with how close those are. I don't think those are close enough, so it's not going to be a zero order. So we're going to have to try something else, and I'm not very good at doing natural log or inverse in my head, so we're just going to have to try all of them until we find one that works. So I usually just go in order. So if it is a first order reaction, the straight line plot is going to come from the natural log of concentration versus T. And you'll notice we don't have natural log of concentration, but we can definitely find that. We are definitely capable. So I'm just going to add another row to my table, and I'm just going to find the natural log of the concentration for a couple of these points. You can also just do it in your calculation of the slope as you go if you don't want to make it a bigger data table. So we'll do the natural log of 1. That's 0. Do the natural log of 0.8, negative 0.22. Then we'll do natural log of 0.4, negative 0.92, natural log of 0.33, negative 1.11. So you don't have to do the whole column of data. You only need to do the numbers you've chosen to use for your 2 points. So now we're ready to find the slope. So we're going to do the natural log of concentration over time. So negative 1.11 minus negative 0.92. Watch out for those double negatives. Over 200 minus 150. Apparently I've decided to do this one first. I guess this is going to be slope number 2. It doesn't really matter, but just so we know which pair of data points I'm using. So that should give me negative 0.0038. Guess we're going to do slope 1 now, since we accidentally did slope 2 first. We'll use these points. Negative 0.22 minus 0 over 25 minus 0. And that should give us negative 0.0088. So there's our 2 numbers that we got. And I'm not feeling very happy. These 2 were different by about 0.007, and these are different by 0.005. And I know what you're saying, 0.005 is a pretty small amount to be different by, but in this case, if they're not almost identical, we're not happy. We want those numbers to be almost exactly identical. So natural log of concentration versus time didn't work, so this isn't going to be a first order reaction. So now we've got to try our second order conditions. Really just doing a lot of work here. Okay, if this is a second order plot, we should have a linear relationship when we plot 1 over the concentration of A versus time. And I realize I wrote 1 over A and this is about B, but you understand. Okay, so I need 1 over the concentration, and I do not have that, so I'm going to have to find it. So we're going to have to add another column to our table for 1 over the concentration of B, which is why I always start my work for these types of problems below the table, just in case I need to make the table a little bit bigger. Okay, so 1 over 1, that is just 1. 1 over 0.8, 1.25, 1 over 0.4, 2.5, and 1 over 0.33, 3.03. And remember, you're taking 1 over the concentration of the original concentration. Make sure you label your column so you're not accidentally taking the inverse of the natural log, because the inverse of the natural log of the concentration versus time is not going to be proportional to anything. It's not going to be helpful. Okay, so let's do our slopes. Let's try and start with the right point this time. All right, so 1.25 minus 1 over 25 minus 0. And that is going to give us positive this time, 0.01. Then we'll do our second set, 3.03 minus 2.5. Over 200 minus 150. And we should get positive 0.0106. Okay, so we'll compare the two numbers we got. And this time they are different by 0.0006. So it's an order of magnitude closer than our other two options. So we're going to say these are essentially equal. So second order is going to be the 1. So it can be a little bit tiring trying to find the order from the data, especially if you end up with the last one you decided to check. If you know how to use your calculator, or if you're good at drawing graphs on paper, feel free to use that. But drawing a precise enough graph to be able to solve for the order from it usually takes longer than just doing this calculation. So this is my recommended strategy for finding the order using data and the integrated rate law.